All right, so in 423, we're looking at the Babylonian method for finding square roots. It's an algorithm that involves iterations, right? So repetition. So it's not the most, let's say, mathematically elegant way of doing it, because it actually lends itself to technology a lot more than some of the other techniques. But there's a lot of number crunching, and it sort of begs the question of like, if technology would be helpful in figuring this sort of thing out, then how on earth did they do it without the use of technology back then? So that's a fun thing to ponder. But the way we handle it is by, so I'll talk you through the algorithm. Square root of a, we're calling that x sub n, where n is the number of guesses that it takes to get to the correct answer. It's not really the number of guesses. It's more like you make a single guess and use the algorithm through multiple repetitive processes to come up with a reasonable approximation of the true value. So here we're saying that that x sub n value should have a power of 2 associated with it. So when it's squared, it should be less than whatever the a value is. And what we would then do is find the average. So when you add two numbers and divide by 2, so or multiply by 1/2, you're finding the average between that nth guess, or well, really our initial guess, as you'll see in a minute, and the a value, which is the value under the radical, divided by whatever that initial guess is. All right. So I mean, there was kind of a lot to consider, but if you look at the steps, it's first make a guess that we call x sub 1. Right. That'd be my first guess. I'll do that off on the side here. All right. So we're looking to find, I think it was the square root of, what's this example? Square root of 5. All right. So just going back to my rule here, I need my initial guess to have a power of 2 that is less than whatever the value under the radical is. All right. So my x sub 1 squared is going to be equal to 4. That's the biggest perfect square value that is less than the radicand here of 5. All right. So that means that my x sub 1 is going to be 2. All right. So my x sub 2, so the first iteration through this process, and the example that we're doing now asks us to do 3 iterations. So this is actually my first iteration, coming up with x sub 2. So that would be 1/2 times 2 plus my a value here, the number that's under the radical, is 5, so 5 over 2. All right, so 1/2, actually I'll just do it all. Not really fair, but I'll do it all in the calculator. All right, so I get 2.25. All right, so then that becomes my new, call it guess. All right, so I know that the value that I'm looking for is somewhere between 2 and 3. Right, and the reason I know that is because 2 squared is 4, which is below whatever the radicand is. 3 squared is 9, which is too big. Right, so I know that if I had a number line here, that I would have a radical 5 somewhere between 2 and 3. Right, and again, that's because radical 4 is equal to 2, and radical 9 is equal to 3, and radical 5 is between radical 4 and radical 9. Right, so it's in there somewhere. What this process does is it inches us along from left to right, going from 2 on up to some value bigger than 2, all right? But it increments us up in such a way that it gets closer and closer to the true value of radical 5. All right, so when I look to figure out x sub 3, it's going to take the average of 2.25. Was that 2.25? Yeah, 2.25. And 5 divided by 2.25. All right, so it's taking the 2.25 and finding the proportion of 5 corresponding with that. All right, so how much of that 5 is accounted for in the 2.25? That's as a ratio. That's what's getting tacked on, and then we find the average. So it's creating an upper bound. All right, so 2.25. I'll just do it all like I did before. I'll do it all in one shot. 1/2 2.25 plus 5 divided by 2.25. All right, so that gets me x sub 3 is equal to, I'll write the whole decimal here, 2.23611. Well, it's 1 repeated after that. All right. If you want to leave it as a fraction, it's not a terrible idea. All right, 161 over 72. With these calculators, I mean, most calculators do this. But if you scroll up, it'll give you a fractional equivalent to whatever the decimal is. So you could write it like that too. But I think we have enough accuracy here that we'll be in pretty good shape. So my next calculation would take the 2.2361 repeated. Sorry, I didn't give enough room for the 1/2. Let me tuck that in there. And inexplicably close the parentheses. I don't know what I was thinking there. So plus 5 over 2.2361 repeated. Right. So here I could just use answer. So 1/2 times answer plus 5 divided by answer. All right. And so I would get x sub 4 equal to 2.236. Again, I'll write the whole thing. 067978. Which they said to go 3 iterations. Sorry, it's super tiny now, but I'm just verifying. Yeah, that's what they did. They rounded it a little bit. But that would be the 3rd iteration because the subscript of 4, and it makes it feel like you did 4 iterations, but that first one, that x sub 1, was our initial guess. We didn't do any math yet. So I did math here, then here, then here. So I did math 3 times. All right, so that makes it a 3rd iteration, 3rd set of calculations. All right. Now, the good thing is, or the good news, I suppose you can sort of consider here, is that if you use the calculator the right way, you can kind of speed through this. All right, so let me show you with the next example here. So we have a radical 11. All right, they said to do, again, 3 iterations, but if you strategically use the answer button, you can kind of zip through this. So if I say, and again, I need to identify the radical value that's just less, or whatever the highest one is that's less than whatever the radicand is. So my x sub 1 squared value, that perfect square value is 9. So x sub 1 is going to be equal to 3. X sub 2 is going to be 1/2 of 3 plus 11 over 3. All right. So 1/2 of 3 plus 11 over 3. All right, 3 1/3. So 3.3 repeated, you could see that's written here somewhere. All right, so then x sub 3 would be 1/2 of 3.3 repeated plus 11 over 3.3 repeated. All right, and this is what I mean by using the answer button, and it's not just limited to this calculator. Most calculators have an answer button, like previous answer. So answer plus 11 over answer. All right. So for this one, I get 3.316 repeated. I hit enter a second time. That wasn't on accident. Because what hitting enter a second time will do on most calculators is repeat the previous calculation. So it repeated the previous calculation of 1/2 times answer plus 11 over answer. So it took my previous answer, which is almost unrecognizable, the 199 over 60, but that is 3.316 repeated. So if I hit enter again, it'll keep going. So here we're actually kind of settling in or converging on what appears to be a pretty solid answer, 3.316624791. And yeah, there it is, rounding it appropriately. But if I want to keep going, I can just repeat that calculation over and over and over again. So again, like I said, 1/2. I think I lost it there for a second. I must have hit a button. But plus 11 over answer. And keep going and do that a bunch of times. Oh, I did it way too many times that time. And it'll settle in on the right answer. All right. So I hit a button along the way, but that's the idea. If you repeat the process over and over again using the previous answer, then you can get it. So I can, like I said, I could do it kind of quickly here. So I started off with a 3 plus 11 over 3. Then I did 1/2 times answer plus 11 over answer. And there is a copy paste option on this calculator. So if you make use of that, you can go. But you can see I hit enter a second time. It gave me the next number. Hit enter a third time. Hit enter a fourth time. Then it starts getting a little crazy. But you can see here that if I scroll over, there hasn't been any movement from the previous decimal iteration to the new decimal iteration, which is basically the calculator saying, listen, I could do this 300 more times. It's still going to give the same answer. So just stop. All right. But once you get to that approximate value that you're comfortable with, then you're good. In most cases, you're looking for a reasonable degree of accuracy. Once you achieve that's the end of it. All right. There's also a Plimpton table or tablet, sorry. So that, if you look at it carefully, it looks very similar to the one of the ones that we did before. The Babylonian formula. If you apply that formula, you'll get another reasonable approximation. Right, but this, like I said before, this is related to a formula that we've already sort of addressed, just a slightly different variation of it. But this is, again, telling us to find a perfect square that's less than whatever the n value is. All right, so my n would be 41. Right, my a squared value would be 36, which means that the a value is equal to 6, and h, where did they put the definition? H, well, they didn't, I don't think they wrote the definition, but it's the distance between whatever the n value is and the a squared value. I'll write it in here. So h is equal to n minus a squared. All right. So it really is just a matter of just figuring out what you'd have to add to the a squared in order to get the n. All right. So In this case, the n value would be 5. So whatever the n is minus the a squared. So then we apply our formula. So I'll write it out in its full glory. Radical n is equal to the radical a squared plus h, which is going to be approximately equal to a plus h over 2a minus h squared over 8a to the third. All right. So radical 41 is equal to radical 36 plus 5, which means a, because 36 is really 6 squared, is going to be equal to 6 plus, oh, I wrote n. Getting late in the day here. Hold on a second. That's h equal to 5. Yeesh. I mean, I used it right, but no excuse, I guess. 5 over 12, 2 times 6 is 12, minus 25 over 8 times a cubed. So 8 times 216, 6 to the third power. 432, 864, 1728. Yep. All right. So 6 plus 5 over 12 minus 25 over 1728. And just like some of the other ones, this is where I tap out with the mental math. So plus 6 plus 5 twelfths minus the 25 over 1728. And we get about 6.4022 if I go 4 decimal places. I'm sure they went 5 or 6 or something like that, but that's what I'm going to leave it at now. And it's pretty spot on, right in the name. Oh, looks like I chose to round it the air quotes right way, right? And the second example is pretty much the same idea. So you can give that a shot and then tackle the exercise set 4.2.